Hi, good morning. Here we are yet again with something more on similarity. Today we are going to discuss something about Thales Theorem, a Greek mathematician who worked very closely and named his work as Basic Proportionality Theorem, which today we know as Thales Theorem. We discussed in our previous session various conditions of similarity. Let's do a quick recap and see. Let's consider the case of triangles today. We say two triangles are considered to be similar if their corresponding angles are equal. Let's check. Checking the angle on the top for the two triangles. Yes, it is matching. Let's check the angle on the left for the two triangles. They match again. Let's see the third angle on the right. Yet again. So we can say that we observe that the two triangles are equiangular. Let's see what are the other conditions. The triangles are considered to be similar also if their corresponding sides are in the same ratio. Let's see. We mean to say side AB and side DE. The ratio of these two sides should be equal to the ratio of side AC upon side DM. Let's see. Let's measure side AB. That's 6. So we write right? Now let's measure side DE. Comes to be 4. So we write okay. Now let's come to the other pair. Oh, that's 6 again. For AC, I'm writing here 6. And for DF, that's 4 again. Right? Now pictorially also we can see whether the two are in same ratio or not. Right? So we can say the conditions of similarity in case of triangles is that their corresponding angles should be equal and their corresponding sides should be in the same ratio. Professor Thales gave us this important result as basic proportionality theorem, which states that ratio of any two corresponding sides in two equiangular angles is always the same. I repeat, ratio of any two corresponding sides in two equiangular triangles is always the same. Same theorem is also represented as if a line is drawn parallel to one side of a triangle to intersect the other two sides in two distinct points. The other two sides are divided in the same ratio. Let's understand this. Let us consider triangle ABC. Here I've constructed DE as parallel to BC. That is to say that I've chosen two distinct points such that line segment DE is parallel to BC, and D and E are two distinct points on the triangle ABC. Now, in the same triangle ABC, I have drawn perpendicular EN to side AD or AB, and I have also drawn a perpendicular DM on the side AE, or you can also say AC. Also, I have joined points B and E, as you can see, and I have joined point D and E. D and C. C. Next, do you recall that we have studied previously that if there are two triangles, say here B, D, E, or if I color it so as to make you understand better, give me a moment. Triangle BDE and CED are on the same base DE, and they lie between the parallels DE and BC. So we studied when this is the condition when two triangles lie on the same base and between the same set of parallels, then they have an equal area. With this concept, we move ahead and see that in triangle ADE, since we have drawn this perpendicular EN and also perpendicular DN, so we can find out area of ADE as half EN, that is the altitude, into base, which is AD, that is area of ADE is half EN into AD. We can also find out area of ADE by considering the other altitude, which is DM. So the area of triangle will be half DM into AE. We also have in this triangle BDE. We can find out its area by considering its perpendicular or the altitude, which is EN, and area of BDE will be given by half EN into BD. Next, we consider CED. And how to find out the area of this triangle? Again, we have to consider its perpendicular, which is DM. So area of CED will be half DM into CE. Now we try to find out the ratio of area of triangle ADE with area of triangle BDE, and also area of triangle ADE with area of triangle CDE. Let's see. Area of triangle ADE is half EN into AD. We found out here. Then upon area of triangle BDE, which is half EN into BD, we found out here, and we get AD upon BT. Next, when we consider triangle ADE and its ratio with area of triangle CED, we get half DM into AE upon half DM into FE, which is nothing but AE upon CE. Right? But we already know that area of triangle BDE is equal to area of triangle CED. Why? Because they are two triangles lying on the same base DE and between parallels DE and BC, so their areas are equal. Now, in the conditions above, if area of ADE is equal to area of ADE, if area of BDE is equal to area of CED, that means these two things, this and this, should be equal also, and so we get AD upon BD is equal to AE upon CE, which is nothing but the condition which Thales proved, that if a line is drawn parallel to one side of a triangle to intersect the other two sides in two distinct points, the other two sides are divided in the same ratio. Let's see in the figure. If a line, which is DE here, is drawn parallel to one side of the triangle at two distinct points, then the two sides are divided in same ratio, that is AD upon BD or DB is equal to AE upon EC or CE. We just proved the Thales theorem. right? If a line is drawn parallel to one side of a triangle to intersect the other two sides in two distinct points, the other two sides are divided in the same ratio. Thank you.